Hey guys, this week we are going to be doing data cleaning, the week you have all been waiting for. Um, so, Sorry about that, had to close my door here. We are really going to be focusing on univariate and multivariate outlier detection, specifically talking about leverage and influence. And I'm going to flip back and forth here a little bit between the presentation and looking at looking at some data. It's some old data that we looked at. It was originally from your text, and we're going to play around with it a little bit and look at how that influences leverage and influence within the regression models. We're fine, and then we're going to wrap up by talking about multivariate outliers and how we assess multivariate outliers. So let's start. So far in this course, we've talked a lot about multicollinearity and ways that we can address multicollinearity if it's a problem within our models. So some of the things that we've talked about is using regression diagnostics such as the variance inflation factor and tolerance. Recall our thresholds there are 10 and 0.1. Examining residuals with the understanding that there might be different forms of data dispersion within those residuals. They may not show homoskedasticity, which is what we're looking for, right? We might see what's called heteroskedasticity. And then we looked at ways to understand this dispersion, either by examining potential interactions when we see heteroskedasticity, when we see spreads of our residuals, or a non-normal distribution of residuals, or trying to fit nonlinear effects with the basic assumption that the effects that we have in our model are almost always nonlinear because nothing in nature is truly linear. However, there are other potential causes of model misfit or misspecification, which have more to do with, I say, messiness than substance. You know, those first issues, having different distributions or different linear associations or nonlinear effects that are part of the substance of your research question, are different than just having problems. We're going to talk about how some of these problems come out. Now, of course, we've talked about multicollinearity and having multicollinear predictors, and this being one of the primary reasons why we center our variables, and how we can go about handling multicollinearity and the different types of multicollinearity. We have not talked very much about outliers. We talked a little bit about graphical descriptions of outliers and how we look at outliers, but we haven't really talked about how we go into testing for outliers and the ways that we examine our data and come to conclusions about what to do with problematic observations or multiple problematic observations. Let's start by talking about leverage. So there are two kind of basic forms of outliers, and the first one is leverage. Leverage outliers tend to be something like this, where you have your nice kind of cluster of linear data, and then you have this person way out here. Now this tends to fall in our linear model, and we're gonna do something here in a little bit to kind of make an example of this, but you can see that observation A or person A falls on this line, but they're way out here. This actually doesn't change our regression coefficient at all, right? Our regression coefficient would stay roughly the same. What it does do, however, is it inflates our R squared for this, right? It makes a more perfect fitting model. It can influence it influence the summary statistics or the standard error of our basic regression coefficients. And we evaluate this using residuals and or the leverage statistic. So we are going to hop away here for a second, and will it let me do this? Oh yeah, I think I can do that. There we go. All right, we're going to come back. Whoops, let's stay here. We're going to talk about leverage, but let's have a look at some data here. So here we have time since PhD and publications, and our this is presentations. We're going to throw another variable in the mix here, and this is just the person's ID. Notice that they correspond to this row right here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 1, 2, 3, 4, 5, blah 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 blah. Okay. So let's do something. Let's go analyze regression linear. Let's remove presentations. We're going to look at the time since PhD as a predictor of publications. Statistics, we want model fit, R-squared, descriptives, part and partials, collinearity, all of the things that we normally request. Plots we're not going to worry about. Save. For right now, let's save a whole bunch of stuff. We'll save Mahalanobis distance, Cook's. We're going to get leverage values. That's what we're talking about right now is leverage. We'll grab some residuals, and then we're going to get influence statistics. We're not going to use these right now, but we're going to come back and compare these after we've run a couple of models. So let's do that. Options, that looks good. Let's analyze that. And so here we are. We have an R-squared of 0.43. We have a regression coefficient of 1.98. It is statistically significant. And here are all of the residual statistics, those values that we had requested. We're not going to talk too much about those just yet. What's more important is let's monkey with this data just a little bit. Let's do something. Instead of 18 and 37, let's, you know what, let's go graph, legacy dialogues, line, oops, cancel, we don't want a line, graph, legacy dialogues, scatter. There we go. We're going to get a simple scatter. And we are going to scatter time since PhD and on our x-axis and publications on our y-axis. So let's get a simple chart, see what that looks like. There's our distribution of our data. Let's double click on it just for a second, and let's just put a simple line in there. Okay. So here's our basic regression equation. 4.73 is our intercept, 1.98 times x is our slope, and actually if we scroll up here, we'll see 4.73, 1.98. Those should map onto our regression model, and they do. They map on perfectly. And so none of these actually look that bad. If we flip over and have a look at just our leverage statistics, that's what we're interested in right now. This is Cook's D. Here's our leverage statistics. We do have a couple that look fairly extreme. We have this 0.36 here and 0.23 here. And if we look at our graph, those are these two right here. This is not causing undue leverage, and you can kind of assume leverage is the dots that fall, or the data points that fall kind of closely together along the x-axis, and all of these do. And then you have some x-axis outliers here. Now they're not outliers as far as the model goes, they're just extreme values on the x-axis, and that's really what we're talking about when we're talking about leverage. So let's try and do something. Let's assume that we had 30 out here, and if we were at 30, then our dot should be right around, I don't know, 50, let's call it 50. So let's go over here. Where is my, there it is. All right, so we are gonna say 30 and 50. That is a big jump here, right? So we changed it to 50 publications, 30 years since PhD. Now we're expecting this line to be like roughly the same. Remember, our slope is 1.98. We'll see if it changes a lot. But we're hoping to put a dot way out here, right? Let's do that, and let's see what happens to our leverage and our statistics now. Analyze, regression, linear. We're going to run everything exactly the same. Now, in something that we expect to have significant leverage effects, we are expecting that our slope coefficients will not change or should not change much. So we had 1.98 before, but that our r squared should change dramatically. So before we had an r squared of 0.43. Let's see what our new r squared is by putting something along that line just out here further. Here's our new model. R squared jumps up to 0.51. That is quite a bit higher. That's almost 10% more variance explained. This is 1.578. Not ideal. I mean, it did drop. My guess is I did a pretty bad job of putting that on there. Let's have a look and see where that line fits. Oh yeah. So you can see I should have actually made this about 60. So let's do that. Let's come back over here. Let's change this to 60. That should put it closer to that line. Analyze, regression, linear, run it all the same. R squared should have gone up more, I'm guessing. Oh, now it went way up. So now it's 0.615 or 0.62 versus 0.43. That's almost 20% more. Our slope, 0.897. That's pretty close. 0.98 was what it was before. And if we graph this out again, graphs, legacy dialog, scatter, let's just have a look here. Yeah, right? Let's plot our line here, see how it looks. Plot our line there. That line looks pretty good, but you can see that this thing here is way out here. Let's go in and let's have a look at something. So before, in our very first model, we had a leverage of 0.36. However, now, in our second model, our leverage was 0.68. That's a lot higher. In our last model, leverage, 0.68 again. That's not so bad. I'm just kidding. It's actually really bad. And so it's not exerting actually a lot more leverage than our second model was. A way to kind of look at this is we can go analyze descriptives, explore, and let's just put leverage over here. Let's put both of the leverages that we've done here. So let's start with this leverage value, and then let's come get the leverage from the last one that we just did, and we hit OK, and let's have a look. Oh, sorry, slow. Okay, here's where we ended. All right, so for this first one, our centered leverage is 0.06. Again, our centered leverage here, 0.06. Standard error is 0.02. Here, our standard error is 0.044. So with this standard error, we can divide any value, any leverage value that we have, and that will give us the number, the z-scores away from the mean that we are. And so our max here is 0.68. If we divide 0.68 by 0.044, let's just go equals 0.68 divided by 0.0, let's even call it 0.05, what the heck, 13 standard deviations away. That seems like it's exerting an awful lot of leverage. If we do 0.36 by 0.03, that's going to be about 10, right? Equals 0.36 divided by 0.03, 12. So even in the first model, it was exerting quite a bit of leverage. The second model also exerting quite a bit of leverage, or the final model. The most important piece here is the change of 20 uh, um, 20% variance explained. You can see in our QQ plot, both of these observations are problematic. Of course, one of them more so problematic. Similarly here, um, we have a box plot that you can see 15 that we changed is really bad there. It gets worse as we move down here. Notice that as we made that one in this second analysis, it actually made the one that wasn't so bad more in line. And then we've got this guy way over here. That's number 15. And in fact, when you have such an extreme outlier, it actually makes the other outlier seem like it's not nearly as bad. So the first way that we go about detecting outliers is by detecting leverage and examining leverage through R squared, our summary statistics, and using the basic leverage statistic to determine whether or not that should be removed, or what you're going to do with it. It doesn't necessarily have to be removed, and we'll talk about that in just a little bit. All right, the next thing that we have is influence. So influence is a little bit different, right? Influence affects your coefficients, your beta coefficients. It also affects your R squared, your summary statistics, your standard error of your regression coefficients, all kind of model related issues. In general, it pulls your regression model in the direction of beta. It can move your intercept. Note here that you would have a nice line here, and you would have an intercept down here. In contrast with this thing here, it pulls your intercept up and it moves your regression line. These influential points are bad values, and they should be eliminated from your sample. Or if they're bad values, they should be eliminated from your sample. You can check these with DF beta and Cook's D, and we're going to do that here in just a minute. So let's hop back over to SPSS, and let's do this. We want to look at our data. So before this was 18 and 37, but in order to make this kind of cranky, let's go 18 and 3. Let's go analyze. So we've only changed one variable. Remember, actually, let's go 18, 37, what it was before. Analyze, regression, linear. Okay. Our R squared is 0.431 right here. Our regression coefficient, 1.98, and it is a statistically significant predictor. Now this is going to be the important piece. Let's go ahead and have a look at our box plot again, or I mean our basic scatter plot, and let's throw our line in there that should be there. There we go. Close that, close that. This is what it should look like, right? This is what our data normally looks like. Let's change just one point. We're going to take this point here and we're going to pull it down here. 18 and 3. Analyze, regression, linear. Remember, our R squared before was 0.43. Our new R squared, 0.07. We changed 1 point and lost our ability to explain 35% of the variance in this model. Our predictor before, our beta coefficient, was 1.98, and it was statistically significant. Now it is 0.785, still positive, but not nearly as strong, and the p-value is 0.342. It's no longer a significant predictor. This means one outlying value changed this model so much that we no longer can explain basically any of the variance, and our predictor is garbage at this point. If we have a look at the graph, that one change produces this. We have this guy down here, And if we want to add our line in there, right, we see a very kind of drastic difference in slope and in intercept. Our intercept now is at 10 and our slope is almost flat. We scroll up here to our last one. Our intercept is close to 0. Pretty steep slope. Very, very different. Let's have a look at these statistics now. So, one of the ways that we can tell if a variable is exerting significant influence, or I'm sorry, significant influence, is Cook's D, and it's called Q here in SPSS. And so we have a range of Cook's D, and Cook's D has a nice cutoff that we don't get with a lot of the other variables, but Cook's D has a cutoff of 1. And none of these have a cutoff of 1. Remember, this was our first regression model that we ran. Then we ran a regression model where we put a variable that was kind of way out there. Remember, this was when we were looking at leverage, and we have a Cook's D now that is higher. And then we tried to recalculate that and make that a little bit closer and to the line of regression. And when we did that, our Cook's D came down. Then we ran another model where we just looked at the exact same basic regression model. We set all of our data back to where it should be. And then our last model here is where we moved Cook's D, or where we moved our variable way down, and we see that our Cook's D is almost 2. This is extreme. We can also look at what's called DF beta, and DF beta looks at the effects on both your intercept, but more importantly on the slope, and it says how much does this one value affect either the intercept or the slope, and if you were to remove it. And in this case, if you were to remove this one outlying value, we would drop our intercept by 8, by a value of, whoops, shoot, I scrolled all the way over here, by a value of 8.13, and we would increase our slope by a value of 1.4. This is telling you what this observation is doing to the intercept and the slope, and that is pretty drastic. You can't make a really good description or really good comparison. These are not cutoffs here, though they can be cutoffs because you can do something like this. We can go graph. Actually, let's go analyze, descriptives, explore. We're going to remove leverage this time, and we are going to look at DF beta intercept and DF beta slope. Let's just have a look at these. And so we can see that the average change in intercepts for any one of those is 0.14 with a standard error of 0.67. Now, if we divide that 8 by 0.67 equals 8 divided by 0.67, and I'm saying 8, it was technically 8.13 if you remember, because that was the effect of that single observation on the intercept. And we can see that this is a z-score of 11.94. That means that that observation is changing the intercept by 11, almost 12 standard deviations. The other piece, the other data here is our slope, our DF beta slope. Where's my DF beta at? Right here. So we had 8.13 minus 1.41. Let's look on our output. What is our standard error for the slope? It is 0.0, we'll call it 0.11. So minus 0.14, oops, equals minus 1.14 divided by 0.11. and it is affecting the slope by about 10 standard deviations, a z-score of 10. That is a pretty dramatic effect on the slope, and so we can conclude from these that at least that observation is having a pretty significant effect on these, right? And if you want, you can do something like this. You can go transform compute variable, and we can say dfi effect. And this is going to give us the effect of the intercept, or the effect of every single observation on the intercept. Real quick, it was 0.67, okay. Divided by 0.67. Come on, slow computer. Divided by 0.67. All right, and let's hop over here. Let's look at our data. We can actually do something after we've done that. We can go graph, legacy dialog, and we can just do a bar chart. Actually, let's not do a bar chart. Let's go graphs, legacy dialog, scatter, and let's go on our x-axis. Let's just put people, ID, and on our y-axis, let's put this effect on the intercept. And this will give us a graph of people by their effect on the intercept. And you can see that we have like a fairly normal distribution of effects on the intercept across people, with one person causing a pretty dramatic effect. I would say that this guy is problematic for the intercept. We can do the exact same thing. Data, transform compute. And let's go DFS effect. This is going to be the effect on our slope. And so we have df beta s phd, and it was 0.11 was our standard error there. Calculate that. And then again, we can go graphs, legacy dialogs, scatter, okay. We're going to do DFS effect this time instead of DFI effect. And what we see here is, again, these are the kind of general effects that we have on the intercept if we were to remove any one of these, and they're pretty close to zero, right? But we have this one person who is exerting a dramatic effect on our slope. This person is problematic for sure, and that is significant influence. And so that is looking at the DF statistics for both the intercept and the slope. You can also look at the Cook's distance to get roughly a similar effect, though Cook's distance doesn't give you the intercept and the slope effects. It just gives you an overall effect. I have the same thing there. Let's open this back up. All right, let's talk a little bit about sources of outliers. So they can come from all sorts of issues. Remember, I said that this is a messy data problem. Usually, these come from some sort of contamination in our observations. It can be an error in our procedures, a problem with how we collected the data, and that falls on us. It can come from inaccurate measurement. So, for example, if you have poor reliability or validity, but especially reliability, think about if you've got people coming in that are getting on a scale, and that scale is not very accurate, you can get really messy data, or possibly there is something going on where a person puts their hand on the table as they step on the scale, and you don't get an accurate measure of their weight. Regardless, you wind up having either an error in the procedure or some sort of inaccuracy in the measurement. Recording or keying errors. If you're using paper and pencil measures and people are just plugging data into papers and pencils, or plugging data into the computer after it's been copied on paper or pencil. It can be problematic. You can have all kinds of recording or keying errors. This becomes a real issue when you're using undergraduate research assistants to enter your data. There can also be problems with calculation errors. So some of the stuff that we do with our data is we wind up making some sort of transformation or adding something or multiplying something. And so it's possible, in fact, just yesterday I was meeting with Sarah and we were trying to work through a calculation error and we eventually figured it out. But you can run into these issues, and this can help you identify. Going through and looking at your influence and your leverage can help you identify if you've made a calculation error or if it's a true error in your data. And then just kind of non-attentive participants, right? People that are just going along, plugging in any answer that they want, not paying attention to what they're doing. Another possible source is rare occurrences. So I can tell you that as someone who does substance use research, this happens. This happens. I have a bunch of people who will drink on average 2 or 3 or 4 drinks a night, and then I have that one person that drinks 27 drinks on a given night, right? And oftentimes this person is a leverage person, but not an influence person. And so I'll see them fitting on the line where they're supposed to be, but accounting for or resulting in substantially more R squared than what I should have because of that person. So how do we do it? What do we do? How do we handle these? Well, we can do a few different things. The easiest and most common way to handle an outlier is to just delete them. Of course, this is a problem because you want to have, you're always trying to strike a balance between giving the best possible explanation of what's going on in the population and having to explain having an explanatory model that accounts for these rare occurrences. If you're able to identify that it's a rare occurrence, you have to make a judgment call about what you want to do with that observation. If you pull it out, you will lose some of the explanatory power of your model, and that could have real-world implications, especially if that rare occurrence is important. If you leave it in and it's not a true rare occurrence, it can lead to model misspecification. It winds up being a researcher call. Either way, the important thing is that you talk through what you did, you present your data, and you make sure that at least in the footnotes, if not in the text explicitly, it says this is what things look like with and without that observation. And this is called sensitivity and specificity. And so it's important to discuss the sensitivity and specificity of your model in the context of influence and leverage, sorry. Another possibility is respecification and or transformations. We've talked a little bit about transformations in the past. If you have data that is becoming heavily skewed and it is resulting in influence or leverage, you may want to think about doing some sort of data transformation. This is a good, solid reason for a data transformation outside of the potential for an inaccurate distribution of residuals or a homogeneous, distribution of residuals. So you might have skewed data. You might do an examination of your residuals and find that your residuals are normally distributed despite the fact that your data is skewed. However, that skew in your data results in high influence or high leverage and consequently higher R squared. It may be worth transforming that data to make a more comprehensive model. Finally, one thing that I really like doing is using more robust approaches. Some of these involve doing things like windsoring, where you chop off portions of standard deviations at the extremes, or you use things like negative binomial models or gamma distributed outcome models. These are models that still fall within the generalized linear model framework, which is the same as OLS, the same as regression and ANOVA, but they allow for a more robust understanding of both predictors and of outcomes. Some of the ways that you can handle outcomes is by changing the outcomes to negative binomial or gamma or so on, as I said. Some of the ways that you can handle predictors is by utilizing things like bootstrapping to recalculate your standard errors, or a jackknife approach to get more appropriate standard errors, or using simple bias correction methods that we see oftentimes in maximum likelihood estimation. All right. So that is how we can handle individual outliers. However, sometimes the case is that we have multivariate outliers. In multivariate outliers, the most common way to at least test for multivariate outliers is to use Mahalanobis distance. I say it's the most common way. I say it's the most common way for people who use SPSS, and so this is what I'm going to teach you guys. Mahalanobis distance is the distance of a point, and the point being any given observation, any given person, from the total distribution of the mean of your data cloud in your full regression model. And this is really your data cloud of residuals. It is a measure of discrepancy that takes into account all of the model predictors. And I want you to keep in mind that all of those model predictors wind up being a degree of freedom for each predictor within the context of this discrepancy or this distance measure. And so this distance measure winds up following a chi-square distribution when that discrepancy is squared. We're going to hop over to SPSS in just a moment, and we're going to look at squaring it in order to do this. But what it ultimately means is you can square Mahalanobis distance, use a chi-square table to determine if your multivariate outliers are in excess of some sort of degree of freedom. So let's do this. Let's look at SPSS, and we're going to leave all of those in there for right now. The way that you get Mahalanobis distance, I'm going to change this back to 37, which is what it was before. You can go Analyze, Regression, Linear, and we are going to add Presentations as another predictor. Now we have multiple predictors in the model. We have a multivariate model. Before, we only had a univariate model or a simple bivariate model where we didn't actually have the Mahalanobis distance under that specification will be very, very close to a simple leverage statistic. If we now change it to this, and we go save, and we select Mahalanobis distance. We've already looked at Cook's and we've looked at leverage, so now we're going to look at Mahalanobis distance. We can go OK. Let's look at our data again here real quick. And so if we come all the way to the end, here are our new values. And here's our Mahalanobis distance, 1.16, 2, 2, 7. We have two extreme Mahalanobis distance values, 5.10 and 5.88. And so if we want to test this to see if these are statistically significant multivariate outliers, we can do this. We can go transform compute. We're going to call this MD2. And we're going to come down here. We're going to find Mahalanobis distance. It's right there. And we are going to square it. Okay. And squaring Mahalanobis distance all it does is add another variable in here for us. It's right here, Mahalanobis distance squared. And now we can go analyze descriptives, explore. Oh, we don't even need to do, let's not do that. Let's just graph this for a second. Let's go legacy dialogues, scatter. Okay, we're gonna leave ID in there, and this time we're gonna look at the distribution of our chi-squared by participant. Okay, you can see we have what look to be like 3 potential outliers on Mahalanobis distance. It's questionable whether or not this is an outlier, but we do know that we have 2 predictors in this model and an intercept, and so we have basically 3 degrees of freedom. So let's come over here and let's look at our chi-square table. You can use 0.05. I like to use 0.01 or even deeper than 0.01, 0.001 if you want. With 3 degrees of freedom at 0.01, 11.34 would be a significant outlier at the 99th percentile. So if we flip back to our data, we have, this value might be close. What did we say it was? 11.34. Let's see what we have here. Oh, we have an 11.79. So this one right here might be a problematic outcome. The other ones, 8 and 15 are almost certainly problematic outcomes. And that's these 2 guys right here, right? Number 8 and number 15. And so we could go and remove these 2 observations. And remember, this is on the regular data. I haven't transformed anything. I haven't changed anything. I went back to 18 and 37 here. And so we do have these same 2 things that seemed like they were problematic. If we actually go analyze, oh, we don't even have to do it that way. We can just look at the Mahalanobis distance. If we only had 1 in, right? If we were to square this, that would be, it's going to be 25. That one's going to be 9. And at 2 degrees of freedom, even here, 9 is going to be close. The other, that number 15 observation, this one would be close. I'm assuming that we square these, right? So this would be around 10, I guess, and this would be 25. This is a definite outlier, right? No matter what we do, whether it's a univariate outlier or a multivariate outlier. Notice, though, that adding another predictor in here makes this actually it makes this one a much worse outlier. This one doesn't change all that much at all. Let's look at the difference between these 2, between 8 and 15 over here. Oh yes, so 10, 48, 44, those look like outliers. Here you have 18, 37, and 60. So you can see that this one winds up being a bit more problematic, probably because of this item. It's way higher here. That would be my guess. But anyway, in this case, I would say we have these 2 oddballs. They were both univariate outliers. This one more so than this one when we looked at univariate effects. However, this one has stronger multivariate outlier effects based on Mahalanobis distance, and I would say that you have good evidence to drop both of those variables, or both of those observations, and then rerun it from there, rerun your analyses from there. So, all right, guys, that is it. That is multivariate and univariate outlier detection. Coupled with the regression diagnostics that we've done before, I believe you guys are set to do full-on data cleaning that looks at multivariate problems as well as outlier analysis. That is it, and I will see you guys in class this week.